All right, we're going to continue our conversation now, moving from our own Milky Way galaxy to other types of galaxies. And so, what we have here is a fantastic image. This is the Andromeda Galaxy. And what's really nice about this galaxy, remember we talked about the Milky Way galaxy being a spiral. Well, the Andromeda Galaxy is as well. And no bar, so it's this nice, beautiful spiral. But what we have here is two of its companion galaxies. So they're both elliptical galaxies. So we have a nice representation of both spiral galaxies here as well as elliptical galaxies. And so I wanted to kick off this with Andromeda because Andromeda is going to become kind of a very special galaxy here as we talk about the different types of galaxies and how we went from having a universe that was just the Milky Way galaxy and everything that was in it was in our universe to one where we are one of billions of other galaxies. All right, so again, this is our own Milky Way galaxy. This, if you can imagine, this is the Milky Way. This is looking up at night. And down here, you can actually see the Andromeda Galaxy as we know it now. But we're going to back ourselves up in time. And this is just going to be considered the Andromeda Nebula, not much different than the other types of nebulas that we can see around the night sky. So all of this is kind of the primary naked eye galaxy that you can see, but we have all sorts of other types of nebula and comets and everything else that appeared and disappeared in our nighttime sky. So from the point of view, right, of earlier times, this was our whole expanse. And so just kind of the way, taking a picture like this and discovering what is what, it was lucky enough that the handle and the part of the Big Dipper was here, that we had these other bright stars to key in on, and right over here in the corner are the Pleiades. So that kind of helped me get my bearings to actually track down and make sure that that was the Andromeda Nebula. So this would have been the perspective, right? And that everything belonged within the Milky Way galaxy, the Milky Way universe. So then how did we get from the Andromeda Nebula and everything just all being within the Milky Way universe to the fact that it was not, to the fact that we were just part of something much, much bigger? And so some of these people might look familiar. Many of you ended up getting a chance to talk about Henrietta Leavitt when we talked about our variable stars and we talked about our Harvard computers. And so you may recognize her in this image. And she was one of the Harvard computers and took lots and lots of photographic plates from other astronomers and then used those plates to help determine patterns in our stars. And this is annotations based on a plate. And you can almost not see the components of the Magellanic Cloud anymore because of all of the little notations that are on there pinpointing different stars and that are in the Magellanic Clouds. And if you did your research on Henrietta Leavitt, she did a lot of research with glass plates from the Magellanic Clouds and was finding all sorts of Cepheid variables there. And so those were the stars where if you mapped them, you could figure out a relationship between the brightness and the period of those stars. So it came up with a luminosity and period relationship. So then that way, if you knew what the behavior of those stars were going to be, that you could move them at any distance and then be able to tell what that distance was. And so what we have down here at the bottom is a background image of the Andromeda Nebula, because what happened is that Edwin Hubble, who you see over here on the lower right, took Leavitt's period luminosity law and started trying to find these variable stars in some of the nebulae so that they could measure the distance to them. And so this is a glass plate showing the Andromeda Nebula, and over here he has reclassified a particular star in between those points is no longer a star but one of the variables. And actually it just says VAR exclamation point there. And then once he applied Henrietta Leavitt's period luminosity law to that variable star was able to figure out that this was much, much further away than something just inside our galaxy, because if it was at the brightness it was supposed to be, to get it that Cepheid to show at that brightness, you had to keep moving it further and further and further and further away. So this was kind of the first step in moving and changing our universe kind of as we know it. So when we think of Hubble, I'm imagining that most people, I would say easily 95% of the population thinks about this lovely, beautiful, wonderful tin can on the right, and not necessarily Edwin Hubble, who you see on the left, and who seems to always have pictures with a pipe. But the Hubble that we're talking about right now is Edwin Hubble and his measurements, very, very precise measurements that he, using Cepheid variables to start measuring out galaxies around us. Later on in this lifetime, we'll continue to use the Hubble Space Telescope to find even more distant galaxies and test some of the things that we're going to talk about in our next lecture about, finding out the motion and the expansion of our galaxy based on what we're seeing in these far, far, far galaxies. I'm sorry, expansion of our universe based on what we're seeing in these very distant galaxies. All right, so let's get back to the basic types of galaxies. So when we're looking at galaxies, and these are being cataloged and observed by astronomers all around the world for hundreds of years, and just becoming more and more refined. And so it was natural to try and wonder if some of these are earlier versions of others. So we have barred spirals, right? So they have a very, very distinctive bar coming through the center, and usually spiral arms, a pair of them, as the primary arm set coming off the ends of the bars. And that's on the upper left. On the upper right, we have kind of the traditional spiral galaxy. In this particular one, we saw earlier, it's the Whirlpool Galaxy, and this galaxy right here, it's being stripped and pulled into the Whirlpool Galaxy. So a non-barred spiral galaxy, and we're seeing this face on and face on. Then we have irregular galaxies, and so this would be like the large and small Magellanic Clouds. And so these are distinctly separate from the Milky Way. Their masses are large enough, and they have a central mass that holds them all together. And so they are, in the case of the Magellanic Clouds, of course, we are stripping those, but we can see these independently, and we can see them around other galaxies as well, as irregulars. The peculiar that you see down here on the lower left, we are going to, for simplicity's sake, at this level, we're going to call them merger galaxies. And so in many cases what you're seeing are galaxies that have been merged or actively being merged, but it may be really hard to see the two or more components that are the two or more players in this merger game, right? So what you have then is something that may have had a very organized structure like a spiral galaxy, but has now been twisted or bent or partially stripped. Elliptical galaxies, kind of best described as footballs in space. So they are not flat like spiral galaxies. They are kind of three-dimensional. They can be in a variety of different shapes, from spherical to football shaped. And they can be of a variety of different sizes. And what's interesting is that you tend to see them as very, very large, but some of the smaller galaxies that we do see are also elliptical, so they do have a wide range of sizes. But the main thing here is the central mass is in the middle of the halo of stars that you see. And then finally you have lenticulars, which are this interesting cross between spirals and ellipticals. So you have a central mass. You do not have arms, but you have what seems to be a disc that's implanted also within a thick halo. So it almost does look like, if you think about a lens like you would have at the end of a telescope. So very, very thick, um, starting to be flattish, central mass, no arms. So again, for spiral galaxies, the tricky bit sometimes is it's easy when they're face on. It was really difficult when they're edge on. You know they're not elliptical, but you're not quite sure if it's a barred spiral, a regular spiral, a lenticular galaxy. So there are times when those edge ons are going to be kind of a mystery. This is a gorgeous little chain of galaxies. So there's tons of galaxies in this picture. You've got a nice spiral right here, you've got a spiral here, but you've got lots of elliptical galaxies, including these guys. You've got a smiley face here, where the mouth is a spiral galaxy, but then these three, the two eyes are ellipticals, and that's a little elliptical as well. It's named Markian's chain. It's in the Virgo area, and this is something you can actually pick up with just kind of a regular decent sized telescope, amateur sized telescope. But there are parts of our observable Milky Way galaxy where if you look in particular directions, you tend to have um, high concentrations of galaxies. And so when we look in this direction, we're looking in the direction of Virgo, Leo, and Coma Berenices. And in that Coma Berenices and Virgo area, we're looking into kind of the Virgo cluster of stars, galaxies. So lots and lots of little galaxies. So with those examples, and we kind of saw those different shapes, Edwin Hubble started kind of mapping them out and putting them into groups. And so for spiral galaxies, he had two major groups, whether that they had a bar, and so these are the SBs down here, or just they were spiral galaxies up at the top. And then the other thing that he was evaluating was how compact are the arms, how twisted are they, or how complex are those spiral arms. And so you'll see out here that they are closer or tighter as they get to the A side, and as they get to the C side, they have opened up. So the arms are wide open. The further you get down this tuning fork, and the closer you get to the base of the tuning fork, the tighter they are. You have the lenticulars, kind of this crossover here, and then you start getting your ellipticals, and then they work their way down the tuning fork from being very flat, right, to football all the way out to kind of circulars. So this has always been kind of called the Edwin Hubble tuning fork classification scheme, because initially this is the set he had, and it just kind of reminds you of a tuning fork. This has now gone through several different iterations and has become much more complicated. But for right now, this is just all we need to talk about the different types of galaxies. So then, let me back up one. If you take a look at these galaxies, we know they're rotating, and so it would be easy to make some assumptions about those rotations. And remember what we learned about our own solar system, right? We took Kepler's law, and the closer you were to the most massive part of our solar system, which was the sun, right, you were going to move more quickly. And so here we have Mercury, Venus, Earth, Mars, and as we move out and move away from the sun, we see a decrease in that orbital speed. You are moving more slowly, right? It's taking you longer to get around that mass that's in the center. So we have an issue here. So we go into looking at galaxies and we make all of the assumptions that that bulge is where all of the mass is going to be. It's where the central mass is going to be. And so remember, we can measure the mass of the galaxy based on the rotational speeds and the distances that we see of objects. So if we can measure things that are between us and the central part of that galaxy, we should be able to come up with a mass for at least that part of the galaxy. And so when we do that, we would kind of expect to see similar things. Your velocity is going to be higher, as you closer you are to the center of the galaxy, and then as you move out, you're going to start to drift down. And we've got to know we have the bulge and we have a bar, so that's going to kind of change the dynamics. The sun does not spread out its mass that way, but you would expect once you get past that center bulge that you would become more like a Kepler curve. And so this blue line is what that expectation would be, that the velocity would drop as we move out. However, the red line is the observed line. So maybe that was just something weird about the Milky Way galaxy. But then here's the rotational curves of several other spiral galaxies, right? And so they're all doing the same thing. As you start to move away from the distance of the bulge, you're flattening out, you're not dropping. So something is going on that either tells us that Kepler was wrong or that we don't understand where the mass is in our Milky Way galaxy. With our solar system, it's pretty darn easy. There's not much competition there. So it seems that that is a very good example of, you know, mass and the distribution of mass right there with our sun, and that the Kepler's law seems to be working fine there. So what that points to is the fact that maybe we don't understand how the mass is distributed in the Milky Way galaxy or in any of these other spiral galaxies that we see. So we need to dig in. We need to figure out what is different. All right, so where is the missing mass? So again, here's a little slide on. We have the bulge. We're out here about 26,000 light years away. And we've got all this halo stars and the stars in there. So somewhere else, we can see the stuff that's here. We can measure the stuff that's here. So that is baryonic mass, mass that you can visibly see, right? And so this, if you add it all up, does not make up enough to account for those strange rotational velocities. All right. Vera Rubin said, okay, well, obviously, if we're missing matter, then but it has to be there. So it must not be anything that we can see. So kind of started the whole discipline of trying to figure out what this dark invisible matter was. And as it turns out, about 90% of the mass that is involved in the Milky Way galaxy that would be needed for our galaxy to move the way it does, we cannot see. So then, if you can't see it, it becomes very, very hard to know what that is. And so this is an active working part of astronomy, people trying to figure out what that dark matter is. I mean, it could be brown dwarfs and rogue planets, but you'd have to have so many of those to make up the amount of mass that you would have. Neutrinos coming from the formation of stars is a possibility, but again, you'd have to have a whole lot of them. Same thing with black holes. Anything, you'd have to have a lot of them. So this is something where we see the mass, right? Because we can see the mass interacting with things like the stars in the arms of our galaxies. We can see the mass interacting, especially in groups of galaxies, where they're being held together, but it's kind of hard to tell why. And we can see it based on gravitational lensing, but we don't know what it is, right? So we have this dark matter. And so this is kind of something that's yet to figure out. So thank you, Vera Rubin, for getting us started down that path. So keep that thought for just a second on that dark matter, because we're going to come back to that. But we're going to go back again to our variable stars and being able to measure distances and being able to measure the distances of things. And this, again, is an image of the Andromeda Galaxy, and it is pointing to a Cepheid variable star. And so this V1 star, this is the star that Edwin Hubble discovered in that glass plate that we saw before, that was the variable star, that was the Cepheid variable that he then used to measure the distance to the Andromeda Galaxy. All right, so that has just given us a new way to a new standard candle. So we talked about it once before, how we can use that for Cepheid variables. Um, and that allows us to measure the distance for nearby galaxies. As we start getting into galaxy clusters, we're going to see this visited again in something called the Tully-Fisher relationship as a new standard. And that is that when you have a galaxy that has a lot of bright material that you can see, it does have more mass, and so it rotates differently than a galaxy with very little mass. So I wanted to tie that piece into it with the dark matter. We still don't see the dark matter, but we can, at least when we look at other galaxies, we can make an estimate on the mass of the light that we can see. And so that Tully-Fisher relationship between what you can see and the mass that's in the galaxy and its rotational is another way that we can kind of judge galaxies that are further away from us. All right, so that's why I wanted to bring that together now when we were talking about that dark matter halo. All right, so another way, again, we had talked about this when we talked about stars, is that other standard candle is a type 1 supernova. And I wanted to show you this because I wanted you to see different examples. And so each one of these different little galaxies is showing a supernova. And so again, the type 1 supernova is the white dwarf with a companion where it actually is bringing in material from those companions and then exploding kind of once it reaches that limit. And we see that very, very distinctive increase in luminosity and then a very rapid decrease, whereas in the massive star supernova, it was a very long decrease. So another one of our standard candles. So if we back up a bit here, we've got our supernova, white dwarf supernovas in there as far as helping us measure further distances, kind of in the same arena as the Tully-Fisher. All right. So then this kind of brings us up to date on measuring those distances to different galaxies, and then the one we'll handle in one of our later lectures is using Hubble's law, and this is for measuring things out to the end of the observable universe. So here we have we've now determined that the Andromeda Nebula is a galaxy all on its own, right? And it is out there and it's at a much further distance than we possibly could have imagined, and that we have Cepheid variables as at this time in this period that for Edwin Hubble in the early 20s, kind of that was the standard candle, that was the furthest distance that we can see. This image that you're seeing right here is newer, right? So this is from the Hubble Space Telescope. And in this image, that point of light right here is the only foreground star. Everything else in this image is a galaxy, right? So you can see all sorts of galaxies of all different types. You've got elliptical, you've got old, you've got spirals, you've got face-on, you've got edge-on spirals over here. You've got lots of irregulars the further you go back. But so that kind of gives you an idea of all of the different types of galaxies that we're dealing with. But there was something else going on, both in theory and in practice, and that was, what does the universe look like, right? So we might have to back things up a little bit here. So when we talk about our universe, we've got the theorists and then we have the observers. So down in the lower part, as far as the theorists are concerned, so Albert Einstein kind of kicked things out, talking about both special and general relativity, how time and mass will interact, and how mass and light interacts, and kind of put together these little thought puzzles, right? He didn't have a way to measure it. This is before Edwin Hubble and Henrietta Leavitt have actually figured out ways to do this measurement, but the little thought and the little problems that kind of came up were, how is our universe going to react? How can light help us figure out what's going on in the universe? How can light tell us about masses that we can see or masses that we can't see? right? And so Georges Lemaitre, and there's three different ways I've heard that name pronounced. So I guess it depends upon if you want to go the French or the Belgian way. But anyway, um, was also took the information that Einstein had put together in his research for those the special and the general relativity and said, look, if we take what you have and we change your formulas a little bit, it we can show that this universe must be expanding. Now, what's interesting about Lemaitre is that, you know, he was a priest. And so for him, he could roll back the expansion to a point where all of this stuff was together, right? And so it had a beginning. And for him, that was great. In fact, that's kind of what he was looking for was for the church, kind of the beginning of the universe and showing that there was a beginning of the universe. But keeping those two things separate, working the science on one side, analyzing what Einstein had put out. And then Alexander Friedman, the Russian, was doing very similar things at the same time. Again, looking at the field notes of Einstein and saying, if what you have here holds, then our universe should be expanding. So then it was up to the observationalists to figure that out. Leavitt gave us the tool, Edwin Hubble did the observations, and Slipher also continued observations and was able to show one important feature. So Hubble was focusing on the distance. Slipher was discovering that the distance was changing. So here's kind of a real quick timeline of that early cosmology, and cosmology is just the kind of the study of how things form and the study of the beginning of the universe. And so, you know, as we pointed off, it was Einstein working on those different theories of how space and time and light and mass work together. Henrietta Leavitt working on light and how the period luminosity law for Cepheid variables. William de Sitter is in there, wasn't in the photographs, but you know, was taking a look at if you had an empty and expanding cosmology, you added the cosmological constant, which we're going to talk about in a minute, that you can kind of create one formation of the universe. We talked early on in the course about the Shapley-Curtis debates, and that was the whole argument around the size of our universe and how those were different, right? And it ended up that the universe is not the Milky Way galaxy. The Milky Way galaxy is larger than we thought, that we are further away from the center than we thought, and that things like the Andromeda Nebula are actually their own galaxies, and they're very, very far away from us. So moving down the timeline, like we said before, Slipher is doing research and distance finding on these nebulae, and as Hubble is actually looking at the distances, Slipher is discovering that there is redshift. And so we know these things are actually moving away from us, which goes back to what Friedman and Lemaitre were saying earlier, that Einstein's equations suggested that there should be an overall expansion of space. And so then things kind of start moving very, very quickly. The more data that we get showing the distances and the fact that they're redshifted, the stronger the proof that that expansion of space is an actuality and not just a theory anymore. And then things kind of back all the way back around again once Hubble actually starts applying the redshifting relationship to his distances and can start to show the expansion. And not only is it expansion, but that the further away you look, the faster the whole universe is expanding. So this idea of here we are in our universe and that the universe is actually expanding is kind of where things start. Where Lemaitre wants to take it is to say if it's expanding out, what happened before, right? So a lot of people Edwin Hubble was working here in the middle. I'm watching things expand away from me. I'm watching everything expanding away from everything else, and the further away it is, the faster it's expanding. And other people were looking backwards saying, okay, well, where did all of this begin? And that's going to be our last unit of this course. But for now, this kind of gives you an idea of kind of where things got um, to bring us to that point of the course. All right, so that's kind of the end of our comparison of galaxies. A couple of things not to forget about. We still have to figure out the whole question about dark matter and expansion, and then that's going to lead us into our next module that reverses expansion, takes it back to discover how did it all happen to begin with. All right, so go back in and take a look at the activities you have in the module, and then the next lecture is really on those active galactic nuclei and supermassive black holes.